All right, welcome. In this video, we're going to continue talking about dynamic programming, and we're going to continue focusing on one-dimensional dynamic programming, where we'll use a one-dimensional data structure to store the solutions to our subproblems. And we're also going to apply this to now a more real-world problem, the longest increasing subsequence problem. It's still a fairly abstract problem, but it corresponds to many real-world problems, and so it's one that we might find ourselves solving sort of as an important part of other real-world algorithms. So let's take a closer look at this problem first. And to do that, I want to just revisit some definitions, mathematical definitions that we may be already familiar with. First of all, the word sequence that we're going to be using in a formal sense here, we're going to take that to mean an ordered set. So we may have other words we might use for this in different contexts, but we're going to use the word sequence for it here. So just as I've got a little indicator here, here's maybe a sequence. Because it's an ordered set and not just any old set. With a normal set, we might use the curly braces. Here we're going to use the round braces to indicate it's an ordered set, again meaning that order matters in the set. Okay. And then from that definition of a sequence, we can also define what a subsequence is. A subsequence, starting with any old sequence here, so say we have our sequence here, S1 up to Sn, is created from any old sequence by deleting some elements. So if we want a subsequence, we just need to delete some elements. And in fact here, if I want to be even more precise, I could say deleting 0 or more elements. So technically a sequence is a subsequence of itself. And if I said 0 or more, I guess that could be 0 up to n elements, because there are n elements in our arbitrary sequence. And if we delete all of them, that would give us the empty sequence, which again also would be a subsequence of the original sequence. Now the one thing we'll notice that in creating subsequences, we are only deleting out elements, so the order of the elements is preserved by this operation. When we delete them out, the subsequence, any of the elements that remain in the subsequence, will still be in the same order as they appeared in the original sequence. This is something that's important because we're going to now apply that to make a secondary definition here that will say a sequence is increasing now if we have this relationship, S1 is less than S2, and so on for all of the elements in the sequence. And then we can kind of put these two definitions together and say, well, now imagine I get any old sequence, maybe a sequence that's not increasing. I can look for a subsequence of that sequence that is increasing. And that's going to be the problem we're basically facing here. Given some sequence, can I find the longest subsequence that is also increasing? So maybe the original sequence is not increasing, but we want to find an increasing subsequence. Okay, so the first problem or question that we might face here is, can we formalize this? Remember, the first step in our dynamic programming, but also in our divide and conquer strategy, and actually any algorithm design strategy, should be to formalize the problem. So let's actually just try that a little bit together. All right, so if we're going to try and formalize this problem, again, we want to set it up as an input and output relationship. So what kind of input are we getting? Well, as we've sort of informally described the problem, our input should be a sequence. And there's maybe a couple different ways that we can set that up. And maybe using, since we're already operating sort of in a mathematical language, I'm going to maybe keep using that mathematical language. So let's treat S like it's a mathematical structure here. It's a sequence, S1 up to Sn, okay, and we'll maybe just say what that is a sequence. And here we might leave it vaguely as just any old sequence, but I think probably here we'll abstract it a little bit and we'll just say it's a sequence of integers. Okay, so we've got a sequence of integers. Now we need to somehow characterize what our output is going to be. Now remember, the output is just what the problem is basically stating us here, the longest increasing subsequence. So we want some subsequence, okay? So how might we do that? Well, again, using the same formalism, there might be a couple ways I could do that. Now, let's just maybe explore one of those ways. I might say, well, hey, maybe I'll call this subsequence S prime. Now I might say, okay, what will the subsequence look like? Now there's a couple of choices I could write here. I could say maybe S1 up to Sk. Here my idea being that K is probably smaller than N because we're looking for a subsequence. Now the problem here, unfortunately, is the way I've written this sort of implies that S1 is a member and also that Sk is a member wherever Sk showed up from up here. Okay, that's probably not something we want to imply. So there's a way that we can avoid that. We could actually go ahead and put some primes on there. Now if we put primes on there, that now no longer sets up a relationship between this, the original list S and this new list S prime. These elements now could be anything. They could even be not integers is the way we've set it up here, unless we add some characterization to that. And in fact, now that I've gone down this path, it's making me think that this is actually going to cause me a little bit more problems, because now I have to put some stipulation over here that says, well, each one of these elements of S prime was originally an element of S. And that's, you know, that's some, yeah, I can do that. It's just now I'm thinking my output's going to be a little bit long. Maybe there's a way that I could write this and not have to, you know, write so many sentences afterwards to express what I mean. So let's see if there's a different way that I can do this, and I'll show you that here. So another way that we can do this is to rely on something that we saw in our last problem, the job selection problem. And I usually give this guy the name A for no other reason than I haven't picked a better name for it. But I usually pick this set A as a subset now of these elements here, 1 to n. Now notice 1 to n are the indexes of the elements in our sequence. Okay, so A, being a subset of that, is picking out which elements we mean. Okay, now A isn't going to imply any order of on these elements that we pick out, but we are going to assume an order that was already implied in our original sequence. In particular, our original sequence we know goes S1, S2, S3, and so on up to Sn. Even though a set's not going to imply that, we can still carry that along with us if we want. So here, A, being a subset of this, must be picking out some of these elements. So any subsequence of S could be characterized by some A, right? Remember, all the elements might be a subsequence. Well, then that's characterized by all of the elements of our index set here, right? Or none of the elements. Well, then we could use the empty set as A. That would select none of the elements. Or any other subset, of course, would end up picking out some subset of our elements above, meaning picking out a subsequence above. Okay, so we can see that this set here, A, is going to select out basically a subsequence. Okay, but we don't want any old subsequence. We need something that tells us that this is increasing. Okay, and actually I've just realized I've made I've overlooked something here, and it's maybe something that's important. So I'm just going to move this down here for a second. What have I overlooked is this part of my problem. I've sort of been sitting here thinking, focusing on how am I going to characterize that as increasing. That's the business I've been working out here. But I forgot about this business here. What does longest mean? Now remember, in our last problem, in the job selection problem, we introduced this idea of a optimization problem. In an optimization problem, you're looking for a minimum or a maximum, or a longest or a shortest. So this here, the longest here, is telling us that this is an optimization problem where we're looking for the maximum length, right? Longest means maximum length. So in optimization problems, one of the outputs is usually the min or the max. And here, I normally call it M. Actually, I might say, hey, well, in this case, we're talking about length. So maybe I'll call it L. Let's call it L. L is supposed to be the length of which? Of this longest increasing subsequence. So I'm just going to save myself a little writing here. I'm going to say the longest increasing subsequence of S. And Now I want to actually return that longest increasing subsequence, and that's where this set A is going to come back in. So I've captured my L, now I've captured that. Let's go back to the problem of saying this subsequence is increasing. So um, maybe there's actually one more I can add here that ties these two together. So remember, L is the length of the longest increasing subsequence, and we want A to be the size of L. So I'm going to say and some set A such that the size of A is equal to L, right? That tells me that I've got the longest one. And now we need to capture that, that this sequence or the subsequence that's selected by A is actually increasing. And there's a couple ways that we can characterize this, and sometimes it takes a little bit of cleverness for us to think of how we might do this. And the way that I've come up with here, maybe took a little bit of cleverness, but I'm not sure how much of my experience I'm leaning on here. But basically I'm going to do one thing. First, remember we said that A doesn't imply order on the elements of our original set. But the index itself does imply order. So, 1 comes before 2, or more, if I is less than j, then we know I comes before j. So I'm actually going to start out there. I'm going to say, and let's pick out two indices, I and j. Let's say that they're in A. And let's assume that for the moment I is less than j. Okay, so we pick out two elements of our set, I and j, and I'm going to assume I is less than j. That means in the original sequence, I came before j. Okay, now what we want is for this sequence to be increasing. If that sequence that we've got here is actually increasing and I came before j in our original set, then the value at I should be less than the value at j. So if I and j are in our set A and I is less than j, then we must have the case that, what do we call it here, S. S sub I is less than S sub j. Okay. If this is true, this last little clause that we've put here, if this is true, then that means our set A picks out an increasing subsequence. Because we could do this for any pair. In particular, the two adjacent ones, right? So 1 would be less than 2, 2 would be less than 3, 3 would be less than 4, and so on. And so this would imply that our entire list, the entire output sequence that we've got, subsequence rather, is increasing. That's what we're hoping for. So, and again, I should mention there's more than one way that we can characterize this, that we can formalize this. And so I've intentionally just sort of done one way that sort of felt natural to me this time. Okay, you notice how I built it together out of parts. I moved things around. I realized I forgot a piece here. And that's sort of the same way you might do it if you're going to formalize a problem that you're working on. Okay, it doesn't just sort of flow out of you all at once perfectly correct. Just like maybe writing a program doesn't do that. You put it together piece by piece, and you sort of, in this case, we're piecing it together with mathematical formalism. That's going to help us. Okay, and again, there could be more than one way that we could try and characterize this, and I've probably characterized it differently on the slides. And so here I've just got sort of a slightly different example on the slides. It looks like I've got mostly the same characterization here, but with maybe a slightly different, looks like notation we use. So remember, I used the sort of mathematical notation that we ended up with up here, S1 up to Sn, but I've used sort of a list or array type notation down here. Of course, nothing changes with the swapping out the notation in a logical or formal sense. So here we've got really the same problem that we had before. Okay, so now that we've formulated the problem, we sort of challenge ourselves, well, can we solve a simple instance of the problem? And usually this is a good way for us to explore a new problem that we're working with and try and discover, hey, do I understand the problem well enough to carry on and try and tackle it as a sort of the main problem, the general problem. So here's an instance, fairly simple. I've kind of designed it in a way to not be super straightforward to find the longest increasing subsequence, but probably you know, with a few passes over with our eyes, we can rely on the very powerful computer we have in our head, our brain, and it actually can do a lot of stuff that we don't even know it's doing behind the scenes. And so this task might be something that you can find that longest increasing subsequence pretty quickly. Now, you might have a few strategies as you're looking for it that you might be going through, and I want you to think about those strategies. These are little baby algorithms. Your brain's already got them built in. Maybe some of them might be useful, and in fact, though, some of them might be a little bit greedy. And let's maybe just explore this again. Thinking about a greedy algorithm. Sometimes greedy algorithms work, and we'll look at that in some videos down the road here. But at the moment, we're just going to explore some greedy algorithms to maybe see that they don't work. Okay, so greedy here, we might focus on two things here. We notice that our problem is asking for really kind of two constraints. Okay, one of them is our optimization constraint. We want something to be the longest, and then we also want it to be increasing. That's the other property that we want our subsequence that we're looking for to have. We want it to be increasing, or we want it to be longest. And we can sort of focus on both of these properties in our algorithm if we want. We want to focus on both of them probably, but we could focus on one or the other. So one thing we could do here is we could look for just increasing. So the idea behind that might be abandon the longest part. Just see if we can find an increasing subsequence. Well, here's how I might do that. I might just start with my 8. That's my first one. Let's see if I can find an increasing subsequence with my 8. Well, unfortunately, most of my numbers here are not greater than 8, so I can't add them to the end of the sequence with 8. I just get 8, 9. That's the longest sequence I can make if I only go for increasing and sort of ignore the longest side. Now, if I like the longest side, then the idea here might be saying, instead of just picking the first element, that was our greedy choice in that last one, let's pick, say, the one that might lead to the longest increasing subsequence. Now, and that might also be the first element, but we saw that didn't help us there. So the other criteria we might pick is maybe the smallest element. Smallest element might lead to a longer subsequence. But unfortunately, again, we get a problem here. The smallest element is 0, and it's actually the last one. So we're really trying to balance two constraints here. We want something that is small. Our first element should be small, but it also should be early in our list. And so and whenever we have two constraints like this, they can pull us in two directions. Small pulled us all the way to this end, early pulls us all the way to that end. So the number we're probably looking for is somewhere in the middle-ish somewhere. We don't know. In this case, in my example, it's actually this one, the one we really want. It's both small and early, right? So it actually is a good candidate. Now, I'm brainstorming here. All these algorithms I'm thinking of are probably not going to work. Okay, this one is small and early, but it could have been up here and still been the one we want to choose, or it could have been up here and not been the one we wanted to choose. So we'll see in a second why that is. But maybe we'll just sort of explore here and say we did want to start with this one. What is the longest sequence we could get? Well, we'll notice now that the 3 fits sort of nicely after that. We go 1, 3, 7 if we wanted. But that would give us then only the 9 after. 1, 3, 7, 9 is of length 4. Again, maybe we've looked at this for a while and said, hey, that looks like the best I can get. Well, what we're facing there is our brain is trying to kind of brute force or try all these different combinations. If it can't find one better than the current one, sometimes we just get tired and we give up. And that's not a great way to work with the algorithm. We shouldn't just try all the combinations unless we have time to do that. But usually we don't have the time to do that. So in this case, and we might notice that the 1, 3, 7, 9 isn't the longest one. In fact, we could go 1, 3, 5, 6, 9. And that one appears longer to me. That's of 5. And here's sort of the final challenge. That one is actually the longest increasing sequence, 1, 3, 5, 6, 9. I know that because I've run an algorithm, and we will, by the end of this video, do that as well. But at this point, just by brainstorming, staring at these numbers, I can't be confident that's the longest one, unless I rule out all the other possibilities. And in fact, for this particular sequence of numbers, there's lots of possibilities. The number of ways we could rearrange this, for instance, is just n factorial. In this case, I think there's 10 there, so 10 factorial. That's a big number. We wouldn't want to try all those different combinations, okay? And you know, the actual number of combinations we need to look at is probably something related to that, smaller, maybe larger, but a little more complicated to figure out. But I certainly wouldn't want to waste my time doing that, especially when we're going to see, foreshadowing, spoilers, that the algorithm we're going to have to run this is not going to be n factorial, exponential times something like that. It's going to be efficient, hopefully, okay? So yes, I mentioned that we did calculate what the longest sequence was, but maybe we can't be confident of that or certain of that without an algorithm that helps us do that. Okay, so one sort of observation that we made already, just in practicing on our simple instance, and again, practicing on an instance like that helps you sort of come up with some ideas. And here's maybe one idea that came to the forefront. We note that for any element S of n, we can only add it to some earlier computed sequence if that other sequence has a smaller number as its last value. And that's a pretty straightforward understanding, is that that's the definition of an increasing subsequence. If we want to add a new number to the end of some already increasing subsequence, that new number has to be greater than the last value in that sequence. Or another way of saying that, that new number has to be greater than all the numbers in that sequence. That's the only way we can put it on the end. It has to be the largest one, right? And this principle is actually going to be very important for us as we come up with our self-reduction. So I do want to, again, maybe try and tackle that self-reduction together. So to do that, I'm going to use a function, and we've been doing this before. We've just been sort of creating a mathematical function. I'm just going to call it LIS, for longest increasing subsequence. And I have to decide what I'm going to put as my argument here. If this were just our program, our algorithm, we would put the input here, but the whole input is not necessary for us. We're only going to consider, so again, let's just maybe on our scratch, or if our input here is this list of n integers, then we're going to consider maybe longest increasing subsequences of shorter versions of that list, and then we can maybe add new elements on as we go. So all we're going to be restricting is this dimension n here. So the only argument I'm going to have for my function is n, which is how many elements are we looking at, okay? So for instance, longest increasing subsequence of 1 then should just give us the longest increasing subsequence of the list that only includes one element. And of course that one should be 1, right? Because S1 by itself is a good element, okay? Then longest increasing subsequence of 2 should be, well, it could be 1 or it could be 2. And it depends on the relationship between S1 and S2, right? If this relationship is true, then it'll be 2. Otherwise, it should still be 1. Okay, now here, I want to stress, and maybe I want to be clear here, I'm going to let my function here, this is a clever little change we're going to have to make our algorithm work. I'm going to say LIS of n should be the length. First of all, that's the only part we're focusing on. Remember in our last video we mentioned that when we're working on these optimization problems using a dynamic programming strategy, we're going to focus on just the optimum, the maximum or the minimum, and then we recover the actual, in this case, subsequence afterwards. So here we're just going to figure out how long it will be, and then we'll try and recover it afterwards. So here we have the longest increasing subsequence. I wanted to express the length of, well, what? Of the longest increasing subsequence, so a little recursion here, but length of the longest increasing subsequence of elements S1 up to Sn. Now I'm going to add something. There's one thing I need to add here that needs to be clever, is I'm going to force my subsequence to end with this value. Otherwise I don't know what it ends with, which makes it hard to add new things on there. So I'm going to add on here, so the length, what I really want to calculate is this, the length of the longest increasing subsequence of elements of all n elements. But to help me calculate that, I'm going to calculate something a little bit easier, which is the length of the longest increasing subsequence of these elements that ends with Sn. And in fact, this last bit is critical and crucial. Okay, so now using this, we can start thinking about what the longest increasing subsequence is going to be. Okay, actually we started doing this a little bit here. This case here where I did this, that said that we could do something like this. Actually, let's set it up. Okay, I don't think I'm going to need all this at the end, but this is going to help us work it out. So if n is equal to 1, we just said, hey, I already know the answer to that one. It's 1. This is where things maybe get a little bit tricky. Okay, so let's do it. Let's do 2. We did this with job selection, so let's try it here. If 2, we just said, oh, but 2, it doesn't, I don't know. I don't know what the answer to 2 is yet. So actually, if I added on here, if I said if n is equal to 2 and S1 is less than S2, aha, then it's 2. But if n equals 2 and S1 is greater than S2, I'm going to assume we have distinct elements, no equals, just to make things easier here. Then the answer is going to be 1. Even if we're only concerned with elements that end with Sn, right? Here, this sequence ends with S2. It has 2 elements in it, so we got 2. But if S2 is greater than S1, the longest sequence we can get that ends in S2 is just S2 by itself. So we got 1. Okay. Now, I hope you already see that if we keep this strategy going, if we do an n equals 3 bit here, we're now going to get a lot of different cases. Why? Because there's lots of different ways that we could arrange our elements out, right? And so I want to kind of step away from that. And in fact, I want to step away from this whole side of things. When we started doing it this way, we basically had a choice of where do we start thinking about our problem. We've got our problem here. This is our list, our S1 up to Sn. And we started at this end. And normally this is a good idea because this is our bottom. And this is our top. So we can either do bottom up. That's going this way. That's what dynamic programming is supposed to do for us. Or we can do top down. And this is our divide and conquer. This is our dynamic programming. Okay. However, usually at this step, when we're thinking about the self-reduction, we usually still want to put our divide and conquer hats on. It usually it helps us think about things from this direction on. So let's do that. Let's put our divide and conquer hat on. Say we're starting at the top, and say, you know, when we have the divide and conquer hat on, we actually get to trust in recursion. What that means is we're going to say, assume they already solved these problems for us. We don't need to worry about that. Recursion will do that for us. We only need to put the last piece together, figure out this last bit. So Sn, what happens in the main problem when n is as large as possible and we're doing our last choice? We just want to decide if we can add Sn on there. And let's use the same kind of logic and idea that we were uncovering when we looked at the bottom. Okay, at the bottom we realized we needed to look at this number, S2 in this case, Sn, and compare it to other values. Was it less than? Is it greater than? Okay, and importantly, we found this. If it was greater than some other value, then we could add it to the end and we got a longer sequence. So for this point, let's just jump down here and let's say there's some other number down here, Si. And for the moment, I'm going to assume Si is less than Sn. Okay, now why am I assuming that? Well, we have two possibilities here. I have Si is less than Sn or Si is greater than Sn. Remember, I'm going to assume they're all unique, no duplicates. Okay, so if this is the case, if Si is greater than Sn, then we were in this case here where we couldn't add Sn to the end of the sequence that ends with Si. Why? Because, well, obviously Si is just too big. So if we can't add it to the end, then this is not a good case. This is not a good sequence that we want to try. We're just going to ignore those cases. Instead, I'm going to look at this case. In this case, for if Si is less than Sn, then if I have a longest increasing subsequence already that goes up to and ends with Si, then I could add Sn to the end of that and get now a new longest increasing subsequence that's one longer, one greater. Okay. And so here we're in this case where Si is less than Sn. And now what I want to do is I want to look up what is the longest increasing subsequence that ends with I. Now remember here, remember this key bit? That ends with Sn, right? So here I'm saying this function here, lis of I, should find me the longest increasing subsequence of elements of the first I elements that ends with Si. Since Si is less than Sn, I know I can add Sn onto the end of that one and get a sequence that is exactly one bigger. Okay, are we done? I don't think we're quite done yet. We got an idea. We now got an expression. Okay, this expression that we've figured out here helps us express what the length of the subsequence would be that includes Sn if we added it to the end of one that ended in Si, assuming this bit. Remember, we ignored these cases. We're not allowed to make lists in this way. So following our rules for increasing, we've decided, okay, if I can add it to the end of this list, how long would that list be? It would be this long. But we just assumed I would exist. There's probably other i's along here as well that also are less than Sn, that we could also add Sn to the end of those lists as well. Well, which one do we want? Which Si do we want? Well, we are looking for the longest one, right? We want the longest such thing. So actually we're getting to the point where I feel like we've almost got our answer here. So the length of the longest increasing subsequence of all n elements must be the max of all of our elements. Now I'm going to try and be careful here. Here I'm going to say over which values of I I'm going to maximize over. Okay, I'm going to start at 1. 1 is less than or equal to I. And I'm going to be careful here. I'm going to go up to n. I can't add Sn to the end of a list that already has Sn in it. Of course, that's impossible. But I could add Sn to the end of a list that had Sn minus 1 in it. That's the first one that's less than n. So I'm going to look at all of the previous elements in my list, and I'm going to pick out the I that has the maximum longest increasing subsequence for I, but such that, and here's where, now here there's actually two ways we can do this, and in fact I want to do this like this. I've said I'm maximizing over all these i's, but I don't want to pick out any such I. Remember, we were ignoring a bunch of i's. I'm scribbling them out, so I'm ignoring them, right? It's only these ones that I want. Si's that are less than Sn. So here I can put it here, the such that. The colon here means such that. So here I'm saying maximization over all the i's in this range such that Si is less than Sn. If I do, I can just close this off and do a +1 at the end. Noticing we're going to +1 on all of them, so we can bring the +1 outside of our max if we want. The other way we can do it is we can actually take this such that and throw it inside our set. Okay, we sometimes do that. And we can write that with this or with this symbol. Okay. I actually like this one, but I think on my slides I've got a different one. So let's go jump to the slides here and check out what we've got on the slides. Okay, I think I've got the same one here. It looks like I got these guys backwards. So I just flipped it around and flipped the sign. I've got the +1 out here, but I put this outside. And that's probably, I can't comment, but maybe it was just easier to write that on the slides, and I can't remember if that's why I did that. Maybe it was just the way I was thinking when I came up with that. But here again, we're reading the exact same thing. The longest increasing subsequence that includes Sn, that ends with Sn, okay, is going to be the max over all of the previous cases, at least in the cases where we can actually legally add Sn onto those subsequences. We'll calculate what the longest increasing subsequence that ends with point I is. We max over all of them, and we add 1. Now, one thing that might strike you here is we don't have any base cases or terminating cases stated in this particular self-reduction. And that's because we're going to be doing something here that actually becomes a little bit more common when we get to dynamic programming, is we're going to start assuming that things that happen out of bounds or things that happen, with a special case, return just an obvious answer. So sometimes we know that, let's just step outside of this problem for a second. Sometimes if we go out of bounds on an array, of course, if we do that while we're programming, we're probably going to get an error or get a segmentation fault of some kind. But when we're working in the realm of algorithms, we don't have to worry about those implementation details. We still think going out of bounds is probably something you don't want to do, but we'll often do something along the lines of saying, okay, assume if you go out of bounds, we just return 0. Or assume if we go out of bounds, we just return infinity or minus infinity. Something that makes sense, that's not going to upset the algorithm. And if we make that assumption, then we don't have to, while we're writing the algorithm, nitpick about, oh, make sure make sure the indices are correct, make sure we're error checking every index, and so on. We'll just throw an index in there and assume that out of bounds does something reasonable. And that's going to be the same thing that we're going to assume here. And what we're going to assume has to do with this maximum. Okay, this maximum, because we've put this extra criteria here, that Sn must be greater than Si, we might have a case where we have an Sn that is never greater than any Si. All of the Si's before us are all greater than us. So we have some minimal Sn. If that's the case, we're actually going to end up maximizing over 0 elements here. And the maximum of 0 elements is truly an undefined, there's an undefined output. We don't know what we should output in that case, which means a couple things. If someone asks you to implement max and they call it with 0 elements, you don't know what the right output is. You should ask them, what do you want me to do in that case? And in this case, we're going to say, again, for the purpose of designing our algorithm, we want to say, well, what's reasonable? What would be reasonable in this case? Sometimes the reasonable thing of the maximum of 0 elements should be minus infinity. Or maybe it should be plus infinity, reasonably in some cases, I don't know. But in our case, it seems like it should be reasonably 0. That is, if we take the maximum of 0 elements here, and then we add 1 at the end, that's saying we would just let Sn be a list all by itself. We are adding it to at the end of an empty list, actually, an empty list of size 0. So we're actually, in this self-reduction, going to make the assumption that this max operator returns 0 if it's called with no arguments. That's what I've said here. And that means we actually don't need any terminating case. Now let's see why that is. Remember what we had written down when we had n equals 1 in our example. We said, well, the output should just be 1. Let's make sure that that happens here. Well, if n equals 1, then it's actually this calculation that gives us 0 elements, because it's saying pick all the i's that are at least 1 is less than or equal to them, but that are less than 1. Well, there is no number that is both less than or equal to 1, or that 1 is less than or equal to and is also less than 1. There's no such number, so there are 0 elements in this max, so this thing returns 0. In that case, adding the 1 is 1. Well, in the case where n is 1, we did want to return 1, so that's correct. Okay, so we've got that correct. So this is a sort of a bizarre, interesting self-reduction where we actually have no base cases as long as we make this very simplifying assumption here. Okay. It turns out also that if we don't make this simplifying assumption, we really get a tangled, messy case, because remember, and this maximization term could have 0 elements in it because our n is 1 here, or because of this term over here, we have an unlucky Sn. That's the minimum of all the elements we've considered so far. If we end up in that case, then we still might end up with 0 elements. We should still write down 1, and technically that's a base case or a terminating case. We might have to go through and initialize that first, and that would be a weird initial pass. All of that is carried out by just making this simplifying assumption that the maximum operator returns 0 if called with no arguments. Remember, that's undefined in the normal case. We're making the simplifying assumption just to make things work for our algorithm. Okay. All right, so we've got this far, but the next step then is to try and convert this into some kind of code, right? Some dynamic programming code. Let's try and do that again. All right, so I'm going to set out my longest increasing subsequence method here, and I'm going to keep in mind that I need a data structure of some kind to store the solution to my subproblems. Now, how long of a data structure, well, am I going to need? Well, we have one subproblem for each of our elements in our list, right? And we didn't consider 0, actually. We might have. There's possibly a subproblem out there where we considered 0, and so we could do that as well. If the length of the longest increasing subsequence of a sequence of size 0 should be 0, so that's something we could add in there. Although we didn't do that in our self-reduction, so let's follow the one that we did. Okay, so let's pick a data structure out here. What should I call it? I'm going to call it L, maybe. Okay, let L, and let's also index it from 1 to n. I like to sort of shorthand it this way, but then I maybe also write, okay, B, an array of what size here? Well, straightforward, looks like it's n here. All right, now, normally, if we had base cases, we would do our initialization phase right here, but we're going to, again, make use of that simplifying assumption about our max operator. We're going to actually jump straight to iteration. So this is an interesting case where we did our declaration. We're going to jump straight to our iteration. We're going to go right into a for loop. And here I'm going to have my for I be equal to 1 to n. We're just going to take the whole thing. Okay. For I equals 1 to n, starting at the first one. Now here I'm going to be filling in L sub I. What is L sub I going to be equal to? Now, here I'm going to, again, I'm writing in pseudocode. I'm writing in algorithm, not code. I don't have to worry about implementation details here. So I'm actually going to go ahead and say, hey, there's a nice, easy way for me to write this. I had already written it in my self-reduction. I'm going to write 1 is less than or equal to, I'm going to be careful here. I'm using i's out here. I don't want to use i's again. I mean j here, and such that, maybe I'll write it down here, such that s of j is less than s of n. And then I'll put here, what am I going to do? I'm going to look up L. It was Li before, but I need to be careful. It's Lj now. And then I'll add 1, because I'm going to maximize over all of those elements. Okay. If I do that, then I can do an n for, and then I'm just going to return. And here, actually, we need to be careful. What do we return here? In our previous example, in the job selection problem, the answer we had was just in the last location. We did this computation, just like in Fibonacci and in job selection. If you're trying to compute Fibonacci number n, your answer was in position n. If you're trying to figure out the earnings for n days in job selection, your answer was in position n. However, that's not what our self-reduction was set up here. Remember, the value that's stored in L here is actually the length of the longest increasing subsequence, yes, of the first n elements rather, yes, also, but that also ends in Sn. Okay, and that's not what we want. We don't want to force the longest increasing subsequence to end in Sn. That was helpful in our calculation here. But we want the longest increasing subsequence that ends with any element, which means this is not correct. So the way we're going to find that is now we're going to take the max over all of our I, up to and including n here, okay, of our Li. Okay, I just realized that I made a typo. I made a typo, an error, a bug. It's a logical bug in my for loop there. And maybe some of you watching along have already found it and said, aha, that doesn't make sense. Okay, but if you haven't, maybe pause, take a second, see if you can find it. If not, all right, I'll show you, I'll point out to you. Okay, now, when we go into this iterative phase of our dynamic programming, we introduce an index here, I. That index I is supposed to stand in for our variable n, where we're writing. In our In our self-reduction, we might have the value n showing up here and there, but when we swap it out, we need to swap it out for I. Now I was really careful in making sure that I used a different index j here than I, which in my self-reduction, this was an I. I did that to not duplicate, but what I forgot was this bit, this n. Here, these two n's are forcing me in every iteration of this loop to only look at Sn. I don't want to do that. At each iteration of the loop, I want to look at the element in position I. So I'm going to make that change now. Right, after changing the n to an I now have the correct code here. And I noticed that in myself, my brain compiler noticed that when I wrote an n down here, and I realized I had written an n up here, and that shouldn't have been an n. Okay. Now, again, that's a quick way or an easy way to avoid that yourself when writing your own algorithms out, is to make sure that when you do this, I almost always do this, I remind myself i's are n's. So if I'm looking at my self-reduction and I'm writing this down for my self-reduction, anytime I see an n, I should be writing I. And then I usually actually use j's for m's if we had a two-dimensional one, and we might see that in a future video. But for now, I've used my j for my I, my original I that showed up. Okay. All right, I do want to do an example using this code to show you how we can solve this, but the last thing I want to do, because having the code here makes it kind of convenient, is to do a quick runtime analysis. Now, if we're sloppy here, and we blur our eyes a little bit, we'll look here and we say, hey, I've got a loop. Loops are usually the expensive part, and there's an n. And I might walk away saying this looks like it's theta n. And that's pretty good intuition, except that it is a little bit sloppy and it's with blurry eyes, because it makes the assumption that what we have here is constant time. And the problem is this max operator, at least with all this business in here, especially this little bit here, this is really, if I implemented this, if I hand this off to a coder now, this is another for loop. And it's a for loop, let's call it j. Let's see, it goes from 1 to I. So we actually have a structure something like this, I equals 1 to n, a maybe plus j equals 1 to I. Looks like I minus 1 if I'm being exactly correct here. But this inner loop's going to give us a bi term. That bi term, when we pop it out, is going to be sort of a Gauss's sum arithmetic series. So it turns out that this runtime, maybe not too surprisingly, with two for loops in it, is actually n squared. Okay, and this is a fairly clever algorithm for this, although I don't think it's the most clever algorithm for this. I think using a map, this is just my own hypothesis, so test this if you like. Using a map to be a little bit more clever, I think we can get the runtime down to n times k, where k is the length of the longest common or the longest increasing subsequence. Okay. And that could be n, so this could still be n squared. But in the case where the length of the longest increasing subsequence is, say, only 4 or 5, then I think we can get it down to this. Now, that's a hypothesis. I haven't tried this out myself. I might be completely wrong there. So try it out yourself and see if you can come up with a more clever algorithm than this. But this one is still fairly clever, since trying all possible combinations, trying all possible subsets. If we just try all possible subsets, there are 2 to the n subsets, and we don't want to do that. Okay, so 2 to the n reduced down to n squared. That's great savings. We like that. Okay, let's maybe complete here by doing a quick example using this algorithm. So here again we have our self-reduction. All right, quickly here we just see that we've got the same code that we just generated together, and we did also comment the runtime was going to be n squared. But let's take a look at a quick example. So again, this is the example that we tried to solve with our brain computers at the beginning. And remembering that our brain computers got a little tired because we didn't want to brute force all possible combinations, But maybe with our algorithm now, we can convince ourselves that we did indeed find the longest increasing subsequence. So to do that, let's start out. Now remember, there's no actual base case or initialization phase here. So every step is going to be going through this loop. But our first loop, the inner loop is empty. Okay, we're picking all the j's between 1 and 1. There are none. So our 8, and remember we assumed that this is going to return a 0 if this is empty. And since this is going to return a 0 if this is empty, we must add 1, return 1. So our first calculation for L is going to be 1. All right. Next, our 1 here, we now do have an element to look at. We have to look at the 8. We can look at its LIS, which is 1. But since we don't have this relationship, our SI is not greater than our SJ. 1 is not greater than 8. Again, our max here is a max of 0 elements. So 0 elements, we get a 1. Okay. Longest increasing subsequence that ends with the 1 is 1. Okay. Let's look at the 3 now. The 3 is not greater than 8. So we don't look at its longest increasing subsequence, we ignore it, but we do look at this one, the 1. 3 is greater than 1, SI is greater than SJ, and so we're going to grab its longest increasing subsequence, which is 1, and we add 1 to it, which is 2. And sure enough, the longest increasing subsequence that ends with 3 is 1, 3 of length 2. Same thing with 7 now. With 7, we're going to look at all 3 of these. And we're going to maximize over any of the ones that were greater than. 7 is greater than 3, so we take a 2. 7 is greater than 1, so we'll take the 1 as well. We're maximizing over these values. 7 is not greater than 8, so we ignore this one. The max of 1 and 2 is 2, so we add 1 more. We get 3. And then again, indeed, the longest increasing subsequence that ends with 7 is 137. Okay. 5, not greater than 7, so we'll ignore it. Greater than 3, so we add 2 to the list we're maxing over. It's greater than 1, so we add 1 to the list we're maxing over. And it's not greater than 8, so we ignore it again. So again, 1, 2, max is 2, add 1, 3. Okay, 2 ignores the 5 because it's smaller, ignores the 7 because it's smaller, ignores the 3 because it's smaller. It's greater than 1, so it puts 1 in its set that it's maxing over. Ignores the 8, 1 is the only value in our set, add 1, we get 2. Okay, continuing, our 6, greater than 2, so we'll add 2 into our set. It's greater than 5, so we add 3 into our set, current winner. Add 6 in, or sorry, rather, 6 is not greater than 7, so we ignore this one. Greater than 3, so we add in the 2, well, we already had a 2 in there. Add in the 1 as well, because 6 is greater than 1. Well, 3 was actually the winner there, so 3 plus 1 is 4. Okay, continuing, 4 is not greater than 6, ignore, greater than 2, so we'll add the 2 in. Not greater than 5 or 7, so ignore those ones. Add another 2 in. Add a 1 in, well, 2 is the winner, looks like we get a 3 here. Okay, 9, greater than everything over here, right? It's our largest one so far, so that means we're really just maxing over all these numbers now. This is a good case where that inner loop is really going to n, right? It's looking at all of the elements. It does look at all the elements. It looks like 4 is the greatest, 4 plus 1 is 5. And then finally 0, kind of an interesting special case at the end. Opposite of the 9 there, it's actually less than all these elements. So we're back to a special case here where this is empty. We maximize over nothing, and we said those return zeros, and 0 plus 1 is 1. So again, it should be very clear here that if we want to return the output here, we don't just return the last element. That's 1. That's saying the longest increasing subsequence of this list is 1. That's just straight up wrong. And indeed, we can see the longest increasing subsequence should be 5. So remember, we're going to take the max over all these elements. Oops, I've got a little typo there. That should be equal to n. But we take a max over all these elements, and we end up picking out the 5. And actually, I've got sort of the recovery here, that when we pick out the 5, we backtrack by just really doing this same math again. That's how backtrack works. Look back at all the previous elements, and we're looking for one with a 4 that we're greater than. So 9 is greater than 6 with a 4. Okay, then the 6 looks back for one we're greater than that has a 3. And in some cases, there may be more than one longest increasing subsequence. So you might track back more than that. So for instance, oh, not this 6. I thought I had one here earlier. Oh, this 4, okay. If we try and track back the longest increasing subsequence from this 4, it could be 4, 2, 1, or it could be 4, 3, 1. There's actually 2 different ones. So how you backtrack is up to you, but in this case it was unique, and there was exactly 1 increasing subsequence. Okay, so I do want to end this video here with just one sort of last comment, which is that what we've been looking at here in the Fibonacci sequence, in the job selection problem, and now in the longest increasing subsequence problem, are 3 algorithms that are one-dimensional dynamic programming algorithms. Now, this comment is twofold. One, these are dynamic programming. These are first instances of dynamic programming. But 2, they all use one-dimensional data structures, meaning a list, to store solutions to their subproblems. And all of them do this, so the amount of storage that we're going to be using here is linear, order n, in our input size, okay, which is common. But we noticed that the runtimes were not always order n. This last algorithm here, the longest increasing subsequence algorithm, actually had an n-squared runtime despite it being a one-dimensional dynamic programming algorithm. So just because you have one dimension doesn't mean you're always going to get a linear runtime. Fibonacci and job selection were, but this case was not. The longest increasing subsequence was not. So, and one of the reasons, or one of the main characteristics of this algorithm that makes it n-squared, is that instead of just looking back at 1 or 2 subproblems behind, we had to look at the whole list. And we saw, at least in this example, 1 or 2 cases where we ended up having to look at the whole list. Meaning, in each iteration, each time we solved the subproblem, we still had to go look at the whole list. So to do that, as a result of that, we ended up with an n-squared runtime instead of a straightforward linear running time. With that said, most of the runtimes for our dynamic programming algorithms are going to be fairly straightforward to analyze, and indeed, this one here is very straightforward to analyze, as long as we remember that this interior loop, or this max operator in here, is indeed a loop. All right. Thanks a lot for watching this video. Stay tuned to the next video where we'll continue talking about dynamic programming. So thanks for watching, and we'll see you in the next video.